Hey guys, last time on 2.5 we talked about the chain rule, which was also the last rule to help us find the derivative of the function in an easier way. Just a quick reminder is that besides that, we also have like another way to find the derivative of any function, which is to go by the definition of derivatives. Okay, and that was mentioned, I remember, in like 2.1 or something like that, where we have to use the quotient rule and then like the limit as delta x or h approaches to 0. Okay, but that's like the long way, the complicated way. Okay, I would highly recommend going to find the derivatives of any function using like these ace rules in here. Okay, so as a quick like review from like like the whole thing from chapter 2, I put like a quick summary in here for all the rules that we learned to find the derivative. It has like the chain rule like embedded in each of the 8 formulas in here. And in the context of higher order derivatives, the standard derivative f prime in here is often called the first derivative. Okay, so this is like f prime, just in case you don't know like how to write, or like English, like how we call it. Okay, so prime here just like for 1. So f prime is not f to the first power. Okay, like this is not 1. This is just like prime, like a apostrophe. Okay, it's like a comma but in the air, like floating in the air. It's not like a 1 in here. So make sure you don't get it mixed up with like the 1. Okay, we call it f prime for like the derivative of f, or like the first derivative of f. And then to find the second derivative of f, we're gonna take the derivative of the first derivative. So that means we're gonna have like f double prime in here. So this is f and double prime. And of course, I'm not gonna test you guys on like how to call them, but then just like just in case you guys not sure on how to call them. Okay, so this is like f double prime, and then we're gonna have like 2 apostrophes for this one. And then another symbol for this one is that we're gonna take the derivative of the first derivative, and then we end up having the second derivative. Okay, and then same thing for the third derivative. We're gonna take the derivative of the second derivative, and we end up with the third derivative, and we're gonna denote it as f triple prime. Okay, so this is f and then triple prime. Okay. Alright, and by continuing this process, we can obtain higher order derivatives. So for example, we're going to talk about the fourth derivative, the fifth derivative, and so on. And then the fourth derivative will be the derivative of the third derivative. And also the fifth derivative is the derivative of the fourth derivative. Okay? So symbol-wise, we're going to talk about like the 5 common symbols for derivatives. So first derivative, we're going to have like y prime in here, or sometime we're going to do f prime of x, or some other time we're going to do like dy dx, and then the symbol of like d dx in here is for like the derivative. So d stands for derivative. Okay, and then if you want, you can split that out. So instead of having a y in here, we can like have an f of x in there. Okay, and lastly, this one is not common use, especially in this class. You're not going to see it in here. But in a sense, well, if you're gonna take like linear algebra, like some higher course in terms of math, you will see this like symbol in here, and a big D in here. The cap D is also stands for the derivative. Okay, but most likely in this class you will see this symbol, this symbol, this symbol, and this symbol. Okay, but not the last one. Okay, so you don't have to pay too much attention to the last one. Okay. And then same thing goes for the second derivative. So we're gonna have like double prime in here, and then f double prime. And then for the d dx thingy, we're gonna have a 2 like for each of them. But then as you can see, the position of the 2 is like different, right? Like on the top part is like d squared, because y has to be separate from the d dx. Okay. And then same symbol in here, but then we're gonna use f of x in here. And then lastly, this one you don't have to like worry too much about it. And then same fashion for the third derivative, the fourth derivative, and also like nth derivative. Okay, so say you're gonna have like the 10th derivative, 12th derivative, and like 20th derivative, or whatever it is. Like when you talk about the nth derivative, we're gonna go with the symbol of parentheses. Okay, so don't do it like y to the n power. Okay, like this is not the derivative at all. this is not derivative, okay? If it were to be like understood as a derivative, we must include the parentheses in here, okay? So as you can see, for the first derivative, second derivative, and third derivative, we all have like primes in there, right? We have like first prime, double prime, and then triple prime. But then for the fourth derivative and like higher derivatives, we're gonna have to go with the parentheses, okay? So for example, if I ask you something like find the fifth derivative, I'm gonna write something like this, okay? Or I'm gonna like find the 21st derivative. It's gonna look like this, okay? So make sure you don't do it like 4 primes in here to talk about the fourth derivative, or you don't do like 5 primes in here to talk about like the fifth derivative, because it's just like, you know, weird. It's gonna take forever if we keep like writing those apostrophes like on top of the y, right? So that's why we have to use the numbers in here. And to talk about derivatives specifically, we're gonna use parentheses around them, okay? So now let me take these out the way. And then note that with each successive differentiation, the degree of the polynomial drops down by 1. Eventually, higher order derivatives of polynomial functions degenerate to a constant function. Okay, and you will most likely to see what it means by doing your example, but let me give you like a quick example in here. For example, let's say if I'm gonna give you a function, say I'm gonna like y equals to x squared minus x plus 10 in here, then the first derivative of it equals to 2x minus 1, right? And then the second derivative, it equals to only 2. And then as you can see, like this one is a stopping point already. I mean, if I want, I'm gonna like ask you to find a third derivative and you're gonna get a 0, right? So as you can see, like eventually somewhere in there, like the derivatives that you're getting only has constant, or I should say like only has like numbers in there. There's no variable in here, like there's no x's in here, and there's no x's also in the third derivative, right? There is an x in the like the first derivative, but then later on, eventually at some point, you're not gonna have any x or any variable attached on the function, on the derivative that you're doing anymore. That's like a special feature in terms of polynomial function, okay? And as you notice in here, what do I mean by dropped out by 1? Like the highest power in here is like 2, right? And then when we take the first derivative, we're gonna get down to like x to the first power, which is just x. And then like we don't even have x in here, right? So we can just imagine that for the second derivative and also for the third derivative, we don't have x. So that means that the power of x in here is 0. So we got down from 2 to 1, and from 1 down to 0. And 0 just stay at 0, right? Like it's not gonna go into like negative power anymore, because we're not gonna do that, okay? And then one of my like personal tips in here is that make sure you just simplify the current expression before you take the next derivative, okay? That will help. For polynomial, it's pretty much just like straightforward, so it's not going to be a big deal. But then, say for my example, you would see how important it is for us to simplify the expression before we move on to the next derivative, okay? So now let me get some of these out of the way so that I have space to do my example. Alright, so for my part, I have to find the fourth derivative of this function, right? So let's talk about the first derivative, f prime in here. Okay, so what is it equal to? Well, we don't have any formula to do with the squared and also the fraction, right? So first, let's rewrite the first function as the square root form. I mean, from the square root form to the power form, and also from the fraction form to the power form, okay? So square root is stand for 1/2, right? So that means we're gonna have x plus 1 to the power of 1/2, and then the other one, it becomes minus and then x to the negative 1, okay? If you're not sure how we end up having the 1/2 and the negative 1 in here for the powers, make sure you talk to me. Make sure you like text me or like email me or schedule a Zoom meeting with me to clarify this one before you like continue to watch this video, okay? And now let's check the first derivative. So it's gonna be 1/2 in here, and then times x plus 1 to the 1/2 power, and then times 1 for the chain rule. If you don't understand why we have like the 1 in here, let me refer it back to like 2.5, where we have like the chain rule with the inside and outside function, right? So inside and outside for this function right here. For the inside, we're gonna get u equals to x plus 1, and then for the outside, we're gonna get u to the 1/2, right? And then from there, we're going to take the derivative of the left-hand side, which is 1, and then derivative of the right-hand side, which is 1/2, and then to the negative 1 over 2 in here. And then u in here, it is x plus 1, right? That's why if I multiply this with this, I end up having this. Okay? And again, if you have any question about the chain rule, make sure you talk to me before you continue to watch this video also, okay? And that's like a little bit explanation for why we have the chain rule right there for the first term. And make sure you know how to do this problem like really well, because you're going to see it on the exam 1 too. Okay? And let me take this out the way. Okay, for the second term in here, what do? We're gonna do like the regular thing in there, because it's not like in a group. So the negative 1, it comes down to the front, so we're gonna get like minus and a negative 1, and then the new power will be negative 1 minus 1, which is negative 2. Okay, and then let me simplify this formula, or like this expression, before I continue to go further, right? So I'm gonna get 1/2 in here, and then wait, I figure out I'm missing like a minus in here, right? Because the new power would be like 1/2 minus 1, which is negative 1/2, right? So that's there. And then what else we get? We get like anything times 1, which is like become itself, right? So I'm gonna get like 1/2, and then x plus 1 to the power of negative 1/2. And then for the second group, I'm gonna get 1, like a positive in there, and then x to the second power. Okay, a lot of people, they might ask me like, why don't I rewrite like the power in terms of, you know, like positive exponent and also like fractional exponent. And I'm gonna tell you one good reason why I don't write them back as like the good form in here, because I need them as the power form so that it's easier for me to take the derivative, like the next derivative, and then you will see why. Okay, just imagine if you were to put it back into like the power form with the squared and everything in here. Well, to take the second derivative, well, now you have to rewrite everything in a power form, right? So that's not worth it, and I'm not going to do that in here. Okay, so for the second derivative, I'm going to do the chain rule again for the first group in there, and again we're going to do the inside-outside method, like the pink table that I should show you guys. If you have any questions on that one, make sure you ask me, okay? I'm going to do it really fast in here. So I'm going to bring down the negative 1/2, and that gives me negative 1/4 in here. And then x plus 1 to the power of negative 3/2. And then chain rule apply in here, which is 1. And then 1 times anything would be just that anything. So I'm not going to rewrite a 1 in here. And then for the second group, or like the second term, I'm going to get negative 2 and then x to the negative 3. Okay, and then the next derivative, I have 3/8 in here. Because I'm gonna like drop out like bring down the negative 3/2 in front, and then I'm gonna do negative 1/4 times negative 3/2 into my calculator, and that gives me 3/8. Okay, and then x plus 1 in here, and then the new power in here would be like negative 5/2, and then chain rule gives us like 1 in here, and then for the second term it's gonna be like a positive 6, and then x to the negative 4, and then last derivative, the fourth derivative. And notice that I didn't write like 4 primes in there, right? I didn't write like 4 apostrophes in there because it's not like the good symbol for the fourth derivative. So make sure you be cautious about like the symbol for the derivatives, okay? And then lastly, I'm gonna end up having this is like negative 15 over 16, and then x plus 1, and then to the negative 7/2 in here, and then this is negative 24, and then x to the negative 5. Okay, and because we had to stop at the fourth derivative, right? So we have to write everything like nicely in the positive exponent, and you know, like no fractional exponent, and call that an answer. Okay, so my answer is gonna look like negative 15 on the top, and then 16 on the bottom, with the square root of x plus 1 all to the power of 7. Okay, and then for the second term, I'm gonna get negative, and then 24, and x to the 5th power on the bottom. And this is my final answer to find the fourth derivative. Okay, and this is what you have to do for your part. And again, if you have like any questions on this one, or if I'm like too fast, if I confuse you, let me know. Okay, and next one we have acceleration. Okay, also the last objective of 2.6 is going to be a quick one. All right, so in 2.3, you saw that the velocity of an object moving in a straight path, neglecting the air resistance, is given by the derivative of its position function. In other words, the rate of change of the position with respect to time is defined to be the velocity. In a similar way, the rate of change of the velocity with respect to time is defined to be the acceleration of the object. So all of that wording just to tell you that, well, the original function, we're gonna get the position function equals to like s of t. Position, I don't know why they call it s, but then we just decide to call it s because the p is already taken for like, you know, like the symbol for point, so we call s for position. And make sure you know one thing about this one is that position is not the first derivative, okay? It's just the original derivative. I mean, it's just the original function. Position function, it has nothing to do with derivative yet, okay? So make sure you don't do any derivatives to find a position function. Most likely, like the problem will give you the position function, okay? And then the first derivative will be the velocity function, where we talk about like s prime of t, which is like, you know, like the first derivative of s. And then the next derivative, if you take the derivative of the velocity, you're gonna get s double prime, which is the acceleration, okay? So this one is the original function, and then we talk about the first derivative, and then from here we take the derivative, and then we get the second derivative, okay? So this one, let's just like remind you guys real quick that this one is the original function, this one is the first derivative, and this one is the second derivative, okay? I kind of like, I highly like stress on this one because in the past, in the test, a lot of people make that common mistake when they take the first derivative of the given function from the problem and they call it to be the position function, and then they continue and take the second derivative and they call it the velocity for some reason, I don't know why, but then that's like the common mistake in there. So make sure you don't do that, okay? Like don't ever do that. Velocity, we're talking about the first derivative, while the original function, it must be the position function, okay? And let me explain why it can be like, you know, like confusing sometimes. For my example, a car is traveling at the rate of 66 feet per second or 45 miles per hour. When the brakes are applied, the position function for the car is given by the equation s blah blah blah, where s is measured in feet and t is measured in seconds. Find the acceleration functions. What is the acceleration at t equals to 50? Okay, so we have two things to do, right? Like we have to find the acceleration in here, and we also have to plug in t equals to 50 into the acceleration function, okay? So we are given a function, right? Like this one is the position function, s equals to negative 8.25 t squared plus 66 t. And if you notice, like this number in here, the 66 is kind of like already like embedded in the formula already. So you don't even have to worry about it anymore, okay? Like it's already there, okay? We just like use it, okay? A common mistake that like for the position function, a lot of people tend to take the first derivative. So for a position function, I don't know why, but then like I said, a lot of people tend to do s prime, and then they got something like okay, so if you take the derivative of this function, we're gonna get negative 8.25 times 2 for the, you know, like the power rule in there, and it gives me negative 16.5, and then a t in here, and then plus 66, right? Okay, this is wrong, okay? Like this is not the position function. This is the position function already because it, well, it's clearly says so, right? So make sure you don't make that common mistake again, okay? So what we just did in here, what we just finished in here is actually the velocity, okay? So this one is the velocity function, okay? Because it's like s prime in here, okay? And to get the acceleration function, we will have to take the second derivative of s. That means we take the derivative of this, and then we end up having negative 16.5 because the 66 will turn into a 0. And then, well, this is the function, right? So we're done with this one. And then, as you can see, I told you from the beginning, for the second part of the question, we're going to plug in 50 for wherever we have t in the acceleration function, right? But as you notice, there's no t in this function, right? It's just like a number. It's just negative 16.5 by itself. It doesn't have anything for us to plug in. So when we plug in the 50 in here, the acceleration will be still negative 16.5 because we don't have anything to plug in. Okay, so for the function, we're gonna have the acceleration equals to negative 16.5, and this is the function, the acceleration function. And for the value, when we plug in t equals to 50, the acceleration value equals to negative 16.5. And because we talk about a value, right? So we must like put the unit next to it, and the unit in here would be, what is it, feet per second, because we go with the 66, not the 45. So we're not gonna use miles per hour. Instead of that, we're gonna do feet per second. Okay, and this is the complete answer for the second part. Okay, and if you have like any question, let me know. Okay, before I caught a day in here, just really quick notation about the unit in here, because this one is meant to be a square on the second, on the second, and I'm gonna tell you why this one is like really like a big deal. Make sure in the test you're gonna get the unit right, because I didn't in the past, and then I learned from a mistake, and I want to warn you guys that the unit is really important for position function, or like position values. Things would be measured in like feet, right? Like either feet or miles. And then for velocity, everything would be measured in like feet per second, or you can do miles per hour for mph. Okay, if you go for that, then the first one will be in miles. Okay, and lastly, when you talk about acceleration, right, we're gonna take it to the next level, and then we're gonna need another like a second in here, so it's gonna be feet per second squared. Okay, so these are like the units for each of the like function in here. That's why we need to have like the 2 in here. Okay, I always like forget that too, but make sure you guys don't do it in the test, because chances are I'm gonna take out some points if you get the unit wrong. Okay, so make sure for acceleration you have to have feet per second squared. Okay, or it's gonna be wrong. And then let me put a star for your part in here to make sure that you guys are gonna turn in for the worksheet. Okay, again, if you have any questions, let me know. Okay, thank you for your listening, and take care and goodbye.